Okay, in this part of the video, we're going to continue simplifying, but we're going to take a look at various problems that have rational expressions. So let's take a look at these three examples, and this is when both your numerator and your denominator are perfect squares. So we're going to rewrite this as two separate factors, and now we can see that both of these are perfect squares, so we really have 9/4. And we're good to go. Our second example, we have the square root of 121/144. So both of these are considered radicands, so I can rewrite this expression and I take the square root of 121, which is 11, and the square root of 144, which is 12, and 11/12 is our final answer. And then the last example here, we have the square root of 361 divided by the square root of 225, and we end up with 19/15. And we can just leave it 19/15. You do not need to change it to a mixed number. So now let's take a look at a few more, but these look kind of similar to the ones we just went over. But if you'll notice, in each of these cases, the numerator is not a perfect square, only the denominator. So I'm just going to rewrite this as separate factors. The square root of 12 is going to be broken down into 4 times 3. The square root of 25 is 5. And then I end up with 2 times the square root of 3 all over 5. And I do not have a radical in the denominator, because remember, that's one of the checklists. You cannot have a radical in the denominator. So luckily for us, this simplified nicely. We're going to rewrite the square root of 98 over the square root of 144. 98 can factor into 49 times 2. The square root of 144 is 12. And then we end with 7 square roots of 2 over 12. The other thing we need to notice is if 7/12 could have simplified fractionally, then we would have. But 7/12 is simplified. And the square root of 2/12, those are two different types of numbers, so we cannot simplify those. We have the square root of 48 divided by the square root of 169. We can rewrite 48 into 16 times 3. Square root of 169 is a perfect square. The square root of 16 is 4 times the square root of 3/13. 4/13 is simplified, so I am finished. Okay, now let's take a set, and I just wanted you to notice that sometimes the numerator is the only radical part of the expression. So this 7 is just 7. And then now we're going to rewrite 28 as 4 times 7. And we end with the square root of 4 is 2 times the square root of 7 over 7. 2/7 can't simplify. The square root of 7 over 7 are two different types of numbers. So you cannot cancel these out. This is your final answer. 6 is not a radical expression, but 18 is, and we can break it down into 9 times 2. We're going to get the square root of 9, which is 3 times the square root of 2 over 6. Now we have the fraction 3/6, which can simplify by dividing each of these by 3, and we end up with 1 square root of 2 over 2, but we tend to not write a coefficient of the understood 1. So your final answer is the square root of 2 over 2. And remember, don't be tempted to try to simplify these. These are two different types of numbers. We have the square root of 80, which is 16 times 5 over 2. We take the square root of 16, which is 4 times the square root of 5 over 2. We can simplify these coefficients, 4 over 2, and we get 2 square roots of 5. And the last type dealing with rational radicals is, it's called rationalizing the denominator. Notice that our denominator is not a perfect square. And remember, we cannot have a radical in the denominator. It's undefined. So we want to create an integer here. And the way we're going to do that is if we multiply the square root of 5 times itself, we're going to get the square root of 25, which is 5. So we no longer have a radical. However, remember, when we're making equivalent fractions, whatever you multiply the denominator, you must also multiply the numerator. So this is really 1. And 1 times anything gives you back that anything. So we have to multiply that both the denominator and the numerator. So this gives us the square root of 15. The square root of 15 is simplified. We can't break it down anymore. So we get the square root of 15 over 5. Again, do not be tempted to divide this 5 into the square root of 15. So we're finished here. Here, we're just going to rationalize the denominator. So rationalize means we're going to make a ratio. So whatever I multiply on the bottom, I must multiply in the top. And now we're going to get a perfect squared number, because when you multiply anything times itself, that creates a perfect squared number. And then we get 70 on top. So we have a 10 in the bottom, no longer a radical. And then 70 can't break down anymore, so we're just going to have the square root of 70. Again, do not divide 10 into the square root of 70. Let's try 2 more. So we're going to multiply the top and the bottom. We don't have to multiply the 2, just the square root of 5 is fine. And then we're going to get 2 times the square root of 25. And then we're going to get 5 times 80. So 5 times 8 is 40, plus your 0. The square root of 5 is 5, so it's 5 times 2. And then I can break 400 down into 100 times 4, and both of those are perfect. So look, this ended up being a perfect square actually. I just noticed that. So 400 is a perfect square. So that's going to be 20. So if we did take the square root of 10, of 100 is 10, and the square root of 4 is 2, that gives us that 20. So we have 20 over 10, and then we end up with 2. Nice. Okay, again, we're just going to multiply by the radical part of that expression. And we get, in the denominator, we get 3, because 3 times the 1 is 3. And we create that perfect square. And then we get 2 times 15 is 30. And then the square root of 30 is simplified. And then when I take the square root of 225, that's 15. And 15 times 3 is 45. And this is your final answer.